So welcome back to the lecture on methods of excitation of DC generators. So this is under the topic of DC generators. On that we have to give the excitation to the generator in order to get the proper supply, DC supply. So this is one of the main area we have to cover and know this. So what are methods of excitation we are having? So DC generators are classified based on how the fields are excited. So there are three methods of excitation we are having. One is permanent magnet DC generator. So in this permanent magnet DC generator, so always we should know the DC generators concept are having field coil and the armature coil. So one in the field coil only we are going to give the current in order to get the field supply. So that is one of the excitation method for the DC generator to give the DC supply. So field coil is excited by permanent magnet in the sense that is replaced by the permanent magnet. Then the second one is separately excited DC generator. So here the field coil is excited by some external means. So normally two coil is there in a DC generator, or in general we can say DC machines. On that DC machines we are having two coils. One is field coil, another one is armature coil. Based on the field coil, how we are going to give the supply to the field coil, accordingly the methods of excitations are classified. So first one is the permanent magnet. This is the permanent magnet DC generator. The field coil is excited by the permanent magnet. Then the second one is separately excited DC generator. So normally the name itself says the field coil of a DC generator is excited by means of the external sources. Then the third one is self-excited DC generator. Here the field coil excited by the generator itself. So no need to give any external sources or no need to use any permanent magnet. By means of the generator we can excite the field coil. So it again and again produce the voltage and give some partial amount to that excitation coil, and it runs to the desired, to get the desired voltage value. So self-excited DC generators can further be classified depending upon the position of their field coils. So normally we already said that the field coil only to produce the magnetic flux in the generator. Field coil only is produce the magnetic flux in the generator. So according to the position, according to the connection of the field coil, we can classify that motor, that generator, into three categories. One is series wound generator, then the shunt wound generator, and the compound wound generator. So what is series wound generator, shunt wound generator, and the compound wound generator? We will see one by one. So this is the first method of excitation, that is permanent magnet DC generator. So as the conceptual point of view, this is the north pole and this is the south pole, and in between the rotor is rotating. So the conceptual and all, you may in the conceptual features of the DC generator, you may study in the construction of the DC generator. So normally we are having a field coil as well as the armature coil. So instead of field coil, we are replacing the field coil as a permanent magnet. So here we are using the permanent magnet as a field coil, and the armature is as usual. By means of the carbon brush, we are giving the supply to the armature coil. In that way, it's rotating and give the desired DC supply. So this is the one method of excitation. That is permanent magnet excited DC generator. So when the flux in the magnetic circuit is created through the use of permanent magnet, that is the explanation for that the above diagram. So when the flux in the magnetic circuit is created through a permanent magnet. So not at all we are going to give any supply, or not at all we are going to use any electromagnet. Instead of that, we are using the permanent magnet. That's why they are called as the permanent magnet DC generator. Then it is known as permanent magnet DC generator. So it consists of an armature and one or several permanent magnets. So here we are having two permanent magnets. So in this diagram, we may see that there are two permanent magnets. In between the permanent magnet, we are having the armature coil. So this type of DC generator does not generate much power. So this type of generator, the field coil which is using the permanent magnet does not produce much amount of fluxes. So based on the flux production only, the generating voltage is there in the output terminal. So if the permanent magnet is somewhat weakened, means we can get the desired voltage. So I can say that this type of DC generator does not generate the much power as we need. So as such, they are rarely found in industrial applications. So these kind of generators we are going to use for the industrial applications. So they are normally used in small applications like dynamos and motorcycles. So in dynamos, in the bicycle, we are using a dynamo to give the supply to the cycle lamp. So such kind of small thing we can use as a permanent magnet DC generator. Then the next thing is separately excited DC generator. These are the generators whose field magnets are energized by some external DC sources such as battery. So by means of some external battery or by means of some external DC supply, we can give the current to that field coil, which is going to produce the magnetic field in the generator. So in order to get the desired voltage at the output. A circuit diagram of a separately excited DC generator shown in the following figure. In the circuit diagram, we are using some symbols, some notations we are using. If in the diagram I may represent IA means that is the armature current, and IL means load current, and V, capital V means terminal voltage, and EG means generated EMF, that is electromotive force. So this is actually the circuit diagram. So this is the field coil, so which is excited separately, and this is the armature one. So here this is the load current. So IL, IA and IF is the main thing to know for the separately excited DC generator. So here we can use the voltage drop in the armature. What is the voltage drop in the armature? I can say that is IA into RA. Voltage drop of the armature is IA into RA. Normally we are giving the supply as 230 volt, sometimes 220 volt DC. the entire voltage is to the armature. In that armature, due to the internal resistance of the armature resistance we are having, that's why we can write the drop as IA into RA. So IA is the armature resistance. Then how can you divide remaining current values? So for that separately excited DC generator, the voltage across the load is nothing but I into RL. So normally, in order to get the voltage value, we are always using the current flowing through that particular device and the resistance of that particular device. So for that load, we need the load value and we should have the current which is flowing through that load. So by means of these two values, we can get the voltage drop across the load. So in that separately excited DC generator, the IL and IA should be the same one. So whatever may be the current flowing from the supply, that is equal to the load current. And the power generated is equal to EV into I. So for every DC generator, we are having the back EMF value. So for the back EMF, we are having the power generation in the generator, that is called EB into I. And power delivered to the external load is equal to V into I. So actually, from the back EMF, we are having the lot of losses, armature copper loss, field copper loss and all. So especially for the back EMF, we are having only the armature copper loss, some mechanical losses. After that only we can get the shaft power and entire mechanical output power as V into I. That is what the voltage we can get exactly at the output, and the current we can draw from the DC generator, that is called the actual external load power. Then the next generator is called, according to the types of excitation, the next generator is self-excited DC generator. So in self-excited DC generators are the generators whose field magnets are energized by current supplied by themselves. So normally we are using the field coil and the armature coil in the DC generator. For that, sometimes we can use the permanent magnet to produce a magnetic flux for the field, or otherwise we can give the external supply to that coil to produce the magnetic flux. But in the case of self-excited DC generators, the field coil of a generator is excited from the supply which is produced on the same generator. From the supply which is produced on the same generators. So initially some small amount of voltage is come to that particular field winding, and it creates the fluxes according to their small voltage level. Then the reaction is keep on continuing up to the desired voltage level we get. So as a chain reaction, due to the residual magnetism, suppose I am rotating the rotor, due to the residual magnetism, a small amount of voltage is produced, some 2 to or 1 to 2 volt. That 1 to 2 volt, the partial value of the 1 to 2 volt again given to that field coil. Then field coil again produces the strengthened magnetic field which is compared to the previous one. Then according to the strengthened magnetic field, now we are having the corresponding voltage is produced at the armature side. So this is keep on continuing until we get the desired voltage. So due to the residual magnetism, that the thing is discussed here, that due to the residual magnetism, so due to the residual magnetism, some flux is always present in the poles. So when the armature is rotated, some EMF is induced, hence some induced current is produced. So this small current flows through that field coil as well as the load, and thereby strengthening the pole fluxes that we are already set. Then as the pole flux strengthen, it will produce more armature EMF. So then and there we are increasing the armature voltage. So first we produce a small amount of voltage due to the residual magnetism. A small amount of voltage due to the residual magnetism. Due to that residual magnetism, sometimes you may get 1 to 2 volt. That the partial amount of the 1 to 2 volt again back to field coil. So from that 1 to 2 volt range or 0.5 to 0.75 voltage range, for that particular value, the field coil is again produces the magnetic fluxes. Compared to previous one, this magnetic flux is somewhat strengthened to produce or to increase the voltage of the armature. So it's keep on continuing again and again. So voltage produced, the partial amount of voltage given to the excitation coil. Excitation coil strengthens the flux from the previous one and increase the voltage level from the previous one. Again this process is continuing until we get the desired amount of voltage. That's why the point is discussed here. As the pole flux strengthen, it will produce more armature EMF, which cause the further increasing the current through the field. So this field increased field current further rises armature EMF, and this cumulative phenomenon continues until the excitation reaches the rated value. If the excitation reaches the rated value, means the rated voltage we can get at the output of a self-excited DC generator. Self-excited DC generator. So in the self-excited DC generator also we are having the 3 classifications. So according to the position of the field coil, self-excited DC generators may be classified as series wound generator, shunt wound generator and the compound wound generator. So series wound generator means field coil which is series to that armature coil. So what is meant by series connection? Each and every device is having its own connecting points, 2 connecting points. Each and every device we are having, for each and every apparatus of electrical apparatus we are having 2 connecting points. So one of the connecting point is connects the other component without any disturbance. That is, we can say these 2 components are in series. Like a way here, the series, that is the armature winding, is in parallel with the field coil. So either we can say the field coil is exactly in series with the armature coil, so without any disturbance. So we can connect only one point of a 2 component. That's why we can say this is the series wound generator. Shunt wound generator means instead of connecting only one point, you can connect 2 points to the armature winding. So we can connect the 2 points of the field coil to the 2 points of the armature coil, then I can say that devices are in parallel. So here the field and armature windings are in parallel. I can say that is the shunt wound generator. Then the next one is the compound wound generator. So the compound wound generators are the combination of the series winding and the shunt winding generators. So series wound generator and the shunt wound generators. The combination of these two gives the configuration of the compound wound generator. So series wound generator, as I already told, in these type of generators, the field windings are connected in series with the armature conductors. That is shown in the further figure. Whole current flows through the field coil as well as the loop. So the entire amount of current from the armature, that is passed on to the load. A series coil winding carries full load current. It is designed with relatively few turns of a thick wire. So in order to carry such amount of current, we have to design a series wound as a few turns of a thick wire. So we can have only the small amount of small turns of or less number of turns, and the thickness which we compare from the ordinary coil is somewhat more in the field coil of a series wound generator. So the electrical resistance of a series winding is therefore very low, rarely 0.5. So in order to pass more current to that armature side from the supply, we should have a less amount of resistance in the series field winding. That's why we are having the value as low as the 0.5. So this is the circuit diagram of a series wound generator. So as I told, so this is the armature and this is the field coil. So this is the armature and this is the field coil. So this field coil is exactly connected. So I already said each and every device is having a 2 points. So series field having the 2 points and the armature having 2 points. So one of the point is connected without any disturbance, means I can say that is the series connected. So here the field coil and the armature coil are connected in series, that is connected to the supply. So here I can say the line current, or as in that is the load current. Here the load current. So the produced line current and the produced load current and the current flowing through that series field winding, that is armature current IA, load current IL and the field current ISC are the same, all are same in the series wound generator, since it is the series connected windings. We can say that in series connection the current is always same. So then and there we are rotating the current value as at the load side we are rotating the current as IL, and in the generator side we can rotate the current as RA, that is armature current, and in between we are having the field current, there we are rotating the current as ISC. So due to the all currents are in same value, I can say ISC is equal to IA plus ISC is equal to IL is equal to I. So three currents are in the same manner. So here I am giving some notations for that from the circuit diagram. Here the RSC is nothing but the series winding resistance, ISC is nothing but the current flowing through the series field. Then RA is nothing but armature resistance value, and IA is nothing but the armature current value, and IL is nothing but load current, V is nothing but terminal voltage, and EG is nothing but generated EMF. So all the things are notated in the circuit diagram. So for the analysis purpose, we can say, as I already told, IA is equal to ISC is equal to IL is equal to I. In general, I can say that is that I can be divided as according to the place of position, that is IA, IL and ISC. So voltage across here, the voltage here, the voltage across the load is equal to V is equal to EB minus IR IA into RE. So the difference of voltage across the load is nothing but the back EMF voltage and the load voltage IA into RA, that gives the terminal voltage. And what is the power generated? The power generated is nothing but EG into I. So actual power generated in the armature is nothing but EG into I. And the power delivered to the load is equal to the terminal voltage and the current which is passing through the load. So at the load side power, I can write PL is equal to terminal voltage V into that load current IA. And next thing is shunt bound DC generator. Shunt bound DC generator. So in these type of DC generators, the field windings are connected in parallel with the armature conductors, as shown in the following figure, that is in the next slide. In shunt bound generator, the voltage in the field winding is same as the voltage across the terminal. Okay, so here I am giving some notations for your reference. RSH is nothing but the shunt field winding, that is shunt winding resistance. ISH is nothing but current flowing through that shunt field winding, and RE is nothing but the armature resistance value, and IA is nothing but the armature current value. IL I can write as load current, and V as terminal voltage, and the EG as the generated EMF, as we discussed earlier. So this is the circuit diagram. I can say this is the shunt bound generator. So I already told, the two wires of a two component connected directly to that next component. I can say these two components are in parallel. So here I am connecting the armature winding coil to the field winding coil directly to them. Then this generator is called shunt bound generator. Shunt bound generator. So the only difference is the current is divided in armature and the field coils. So in the series field generators, we are having the same current under all the points, in the load point and in the field point as in the armature point. We are having the same current value. But in the case of shunt bound DC generator, the current is divided. So the line current here is divided into, so this is the load current, the load current is divided here into IA plus ISH. So this IA is nothing but ISH, that is IL minus ISH. So the IA only divided into two parts here. So here the IA is coming and it is divided into the load current IL and the field current ISH. So I can say IA is equal to IL minus ISH. IL minus ISH. So here armature current is dividing into two parts. One is shunt field current ISH that I already discussed, and the another is the load current IL. So IA is equal to ISH plus IL. So in the slide I said that IA is equal to IL plus ISH. So both the current is from armature current. That's what this equation denotes. So the ISH current and the IL current both are coming from the armature current. So the armature current is divided into ISH plus IL. So the effective power across the load will be maximum when it will be maximum. So the effective power across the load will be maximum when it will be maximum. So it is required to keep the shunt field current as small as possible. So in order to get the maximum power value, we are in a position to keep the shunt field current as small as possible. So for this purpose, the resistance of the shunt field winding generally kept high, that is nearly 100 ohm, and the large number of turns are used for the desired EMF. So our ultimate aim is to supply or deliver the load current without any huge losses inside the motor. So in the shunt field self-excited DC generator, the shunt field is parallelly connected to the armature. Suppose I am producing some voltage, some 230 volt. The partial amount of the 230 volt, say 150 volt, is going to the shunt field winding, means the remaining 150 volt only I can get at the output. That is not at all a good one for the good machine. So in order to increase the efficiency, we have to pass the more number of current or the effective voltage at the output. We have to keep the shunt field resistance as high as possible. So nearly they are noted as 100 ohm. So these are some equations while we are analyzing the shunt bound generator, that is the shunt field current is equal to ISH. We have to notate as ISH, that is equal to V by RSH. So as per Ohm's law, I can write I is equal to V by R. In the shunt field winding, the voltage is directly applied to the shunt field. That's why I am putting the voltage V as in the numerator, and I have to find the corresponding shunt field current only. I have to use that's why I am using RSH as a resistance value. That's why I am writing ISH is equal to V by RSH. Then the voltage across the load is equal to, I can write V is equal to EG minus IA into R. So since we are having the field coil in a parallel mode or parallel connection, I can write the losses only for the armature winding. So the generated EMF is wasted in the armature as IA into RA. The remaining voltage I can get the output as B. Then the power generated is equal to, I can write the power generated is equal to EB or EG into IA, generated EMF in the armature. That is the power generated. And the power delivered to the load is equal to PL into V by IL. So the EG/IA gives the voltage before the losses, and the PL is equal to V into IL gives the power after the losses which is occurring in the DC generator. So we are having so many losses: stator core loss, stator copper loss, rotor core loss, rotor copper loss, and windage and friction losses. So after considering all these things, these losses, I can write the power delivered to the load is equal to P is equal to VL V into IL. V into IL. The next one is the compound wound DC generator. So in the compound wound DC generator or in the series wound generator, we are having the output voltage is directly proportional with the load current. So in series wound generator, the output voltage is directly proportional with the load current. In shunt wound generator, the output voltage is inversely proportional to the load current. That is the main thing we are having the differences. So in the series field winding, the output voltage is directly proportional to the load current, and in the shunt field winding, the output voltage is inversely proportional to the load current. According to the equation, we can say like this: a combination of these two type of generators can overcome the disadvantages of the both. So we may have the disadvantages for the series field winding as well as the shunt field winding DC generators, that will be overcome by making the combination of the series field winding and the shunt field winding in this same machine. So that's why a combination of these two types of generators can overcome the disadvantages of the both. This combination of windings is called compound wound DC generator. So I have to combine these two windings in order to rectify the disadvantages which I am having in that series as well as in the shunt field winding or shunt wound generator. That configuration, the new configuration is called compound wound DC generator. Compound wound DC generator. So compound wound generators have both series field winding and shunt field winding. So one winding is placed in series with the armature and the other is placed in parallel with the armature. So as I already discussed, the phenomenon or combination of the series field winding or shunt field winding is present in the compound wound DC generator. That's why we are writing this point like this. So this type of DC generator may be of two types: short shunt compound wound generator and the long shunt compound wound generator. So how this shunt field winding is connected, either which is parallel to the armature or the combination of series connection or series field winding and the armature. So two type of parallel connection we can make for the shunt coil. So shunt coil is only parallel with the armature, means that is the short shunt DC compound generator, and the shunt field coil is parallel with the combination of series field winding and the armature winding is called long shunt compound generator. So as we discussed, short shunt compound wound generator, the short shunt compound wound generators are generators where only the shunt field winding is in parallel with the armature winding, shown in the figure below. So this is actually the figure for the compound wound DC generator and the short shunt configuration. So in the short shunt configuration, this field coil is only parallel with the armature winding, only parallel with the armature winding. It's not at all affecting the series field winding. It's not at all affecting the series field winding. So here I can write series field current is equal to ISC is equal to IL. So in the short shunt DC generator, from the diagram itself I can say, so this is the IL actually. This IL directly come to that field winding, ISC. So I can say ISC is equal to IL as per the configuration we made. And the shunt field current is equal to V plus IARA by IRSH. So V plus ISC RSC. Since we are having the series field winding in series with the supply. So here this is actually the V value. After the V, I can have the drop for the series field winding. So what voltage I can get across the armature? This voltage minus this drop. So this voltage is nothing but V, and this drop is nothing but ISC into RSC. That's why I am writing V plus ISC into RSC is the exact voltage of the shunt field winding. That exact voltage by the corresponding shunt field resistance gives the shunt field current of a compound generator. Then what is the value of armature current? Armature current is nothing but IA is equal to ISH plus IL. Then the voltage across the load is equal to V is equal to EG minus IARA and minus ISC into RSC. So as in the diagram we can write as V, then subtracted by, that is the voltage across the load is equal to the EG, generated EMF, less by the armature drop and less by the field drop. So we are having the armature voltage drop and we can have the field voltage drop. So that generated EMF is drop on the armature as well as in the field. I can write EG minus IARA minus ISC into RSC. Then what will be the power generator? That is equal to EG into IA. So this power generator is always same for all kind of motors. Generated power is equal to the generated voltage into that armature current which is flowing in the machine, that is EB into IA. Then power delivered to the load is equal to V into IL. So this is also same for all kind of motor. All kind of motors. And this is the circuit diagram for the long shunt compound wound DC generator. So here this field coil exactly parallel to the series combination of series field winding and the armature. Okay, series field winding in the armature. So the field coil which is parallel in series combination of armature as well as the series field winding is called long shunt compound wound generator. So long shunt compound wound generator, DC generator or generators where the shunt field winding is in parallel with the both series field and the armature winding as shown in the figure below. So here are some equations in order for the analysis purpose. The shunt field current is equal to ISH is equal to V by RSH, which is discussed in the previous motor. Then here the armature current IA is equal to series field current. So the configuration is now changed. Then the armature current is equal to the series field current. Then ISH is equal to ISC is equal to IL plus ISH. Here the field current ISC is equal to load current plus shunt field current. Then the voltage across the load is equal to V is equal to EG minus IARA minus IAC RSA. So in that way we can calculate the voltage across the load of a compound bound DC generator, which is long shunted. So then the power generated is equal to PG is equal to AG into IL, as we discussed earlier, and the power delivered also PL is equal to B into IL. So that's all about the thing. Thank you very much.